I'm going to start our video. Welcome to our Phase 2 inaugural SHIELD webinar. I'm Nick Gross. I'll be running the Zoom and mostly trying to stay in the background. We have some excellent panelists today to discuss 45 years of discovery of the Voyager mission. Before we get into that, we've got some shameless plugs for the SHIELD Drive Center, which, as I said, just recently was awarded its Phase 2 funding. And the SHIELD Drive Center is devoted to studying the outer heliosphere and its interactions with the interstellar medium, looking at its modulation of cosmic rays and the interactions with the stellar medium and creation of energetic neutrals that penetrate into the inner heliosphere and are measured at IBEX and at soon IMAP, and also some of the details of the Voyager data that we've been getting back recently. These are the SHIELD institutions, so we've got 10 institutions that have SHIELD researchers at them, so it's a broad cross-institutional collaboration. Our broadening impacts effort, so we consider these webinars not only to be part of our science mission, but also our broadening impacts mission. And our major goal in our broadening impacts mission portion of the SHIELD Science Center is to grow a diverse and inclusive leaders in the community. And so we, in Phase 1, we worked across a wide variety of audiences, and in Phase 2, we're going to continue to do that, but also then develop our leaders who will be the potential leaders and PIs for new missions, including Interstellar and other missions that are upcoming. Few other broadening impacts efforts that we have. One is we are going to continue collecting testimonials from people for our You Can't Be What You Can't See effort, where particularly early career and emerging scientists, but also senior scientists can share their experiences and their testimonies and their backgrounds and tell their science story and tell their personal story and their personal journey through that. For more details and more information on that, you can contact us at shieldoutreach@bu.edu or contact myself. I'm the Deputy Director for Broadening Impacts, or Sandlin Buxner, who is the Director for Broadening Impacts and is on our the webinar today as one of our guests. And she may say a few words at the end. Finally, just some next events. First, we are going to continue our webinar series into the fall and then into the spring. We're skipping September because everybody's still just getting back into the swing of things. We are working on scheduling a speaker for, we got a couple of speakers possibly for October, but we haven't fixed that yet. Vicky Calagera from Northwestern University is going to be our speaker on November 18th. And then we'll start back up in January with Peggy Shea, who has long experience with the space weather and the heliophysics community. Finally, September Social Hour, we're going to restart that for young, early career and emerging scientists to talk about their experience, share their challenges, share their experiences, and provide a support network for everybody. Okay, and then finally, this is where you can reach us at Shield. If you search the web for Shield Drive, you will find that you will get driving lessons. That is not what we want, so you need to do either Shield Drive or NASA Shield Drive or Shield Drive Science, and you will find us on the web, and you'll find us on Facebook that way, and they were on Twitter, we're Shield_Drive. And you can also reach us at the Shield outreach at bu.edu. All right. So that's enough of that, unless Marav has anything that she wants to emphasize right now, or maybe
Oh,
later.
wonderful.
Great. All right. I'm going to turn it over. So our speaker order for today, we're going to start with Nikki Fox, and then from NASA headquarters, and then Linda Spilker from JPL, and then we'll end with Marav. Each of our speakers will take about 10 minutes to tell some of their experience, and then we will also take, after that, we'll take questions or from the audience. And so feel free to populate the chat with questions at any time. And I will, if it's appropriate, I'll interrupt the speakers while they're speaking, but it may be that they are, we can also save them for the end. So at this point, I'll turn it over to Nikki. Okay, great.
All right, thank you. Can you see the screen okay?
Yes, just fine.
All right, thank you so much. And thank you for the invitation to join you today. It's always exciting to talk about Voyager. And I wanted to start off by really showing you the position or the importance of Voyager in our Heliophysics System Observatory. And so for those of you who may not know me, I'm Nikki Fox. I'm the Division Director for Heliophysics at NASA headquarters. And as part of my things I get to play with every day, here are the 20 operating missions, 18 missions in formulation or implementation, and one that we have under study that's not actually on there. And you can see at the bottom there, our Voyager spacecraft on our fleet chart, nicely circled in white. But it's always really hard when you look at these kind of things to, I think, really get the perspective of just how far out Voyager is. And so if this animation will play, let's fingers crossed it'll play. We start from the sun, accelerate rapidly outwards beyond all of the planets, way beyond the orbit of Pluto, out into our heliosphere. And basically what you're looking at there is the heliosphere shown as kind of a windsock shape, as it protects the boundary there, protecting us from the vagaries of interstellar space. So it's basically a cavity that's built up by the solar wind as it presses outwards and then intercepts with our local interstellar medium. But that's how far out. I think it gives you just a good idea of how far away our Voyager spacecraft is. If I show you it maybe with a different perspective and take you all the way out to the outside our Milky Way, let that Milky Way rotate into place, and then you will also see where Voyager sits kind of with respect to the galaxy. So we sit in one of those spiral arms, and you'll see that zooming in now on the heliosphere from sort of the outside in. So again, I think it just gives a really nice perspective of where Voyager sits in our solar system. And so let's talk about the Voyager spacecraft themselves. They are, of course, the furthest spacecraft from Earth. They were launched in 1977. I know a lot of folks think that the New Horizons spacecraft is a long way away, but the New Horizons spacecraft has quite a lot of catching up to do to get out to where our Voyagers are. The extended mission, this is sort of, they're in their extended mission. They had their initial mission concept, which was to fly by all of these planets, and they did their sort of great planet tour on the way out. And then we realized as they were moving out towards the outer heliosphere that we could do some incredibly useful interplanetary and possibly interstellar studies looking at the fields, particles, and plasma as we get out into the outer heliosphere. And so the mission was transferred over to the Heliophysics division, which we're delighted to have. And those spacecraft continue their exploration exploration of the solar system beyond the planets, all the way out to the very edge, the outer limits of where the sun's kind of sphere of influence stops and interstellar space starts. And so really, really excited about all of the science that our Voyagers do. So as I just said, it was congratulations to our longest lived mission. They've been doing 45 years worth of discovery. And you can see there Voyager being prominently featured on the July issue of Scientific American. So always great to see our spacecraft being recognized for all the wonderful things they do. The Voyagers definitely remain on the cutting edge of space exploration. They are, of course, managed and operated by NASA's Jet Propulsion Lab, and they are the only probes to ever have explored any regions of interstellar space. So really exciting about all those things that they do. All right, let's go to the next chart. So the interstellar mission, so if we focus on that in particular, our Voyagers continue this cutting edge Heliosphere Discovery. In 2012, Voyager 1 flew beyond the Heliopause and entered interstellar space, of course, making it the first human-made object to explore this new regime. The exciting thing that I'm going to talk about, and I was asked to sort of talk about my own personal excitement, or the thing that I was most excited about with the Voyagers, and that was actually when Voyager 2 crossed the Heliopause in November of 2018. It's exciting because it went out in a completely different direction to Voyager 1. So if you look at that little cartoon there, you can see the placing of both Voyager 1 and Voyager 2. And I'll just note that when New Horizons does get out towards the termination shock and out sort of beyond that, it will be coming out right down the nose. And so that will also provide us really great data in the interstellar medium, kind of in that sort of nose region in the center there. So they're both out, and the mission is continuing to characterize our outer solar system and the outer limits of the sun's magnetic field as it goes sort of beyond the flow of the solar wind. But this is the graphic I was sort of most excited about. So as I noted, the Voyager actually left the or crossed the Heliopause in November of 2018. And so I actually started as the director in heliophysics in September, the beginning of September of 2018. And it was a very exciting time. One of the first things I actually had to deal with was this particular excitement about the encounter of this boundary. So Voyager 1 actually had an instrument, it had the same instruments on it, but their plasma instruments, so the one that really measures the solar wind, was actually not working when they crossed the Heliopause. And so it was difficult to actually say exactly when we crossed that boundary because we didn't have the sort of smoking gun data set. But Voyager 2 had the solar wind instrument still working. And the only problem was that we could only take the data if we were actually in communication with Voyager 2. Now, Voyager 2, if you remember, is down in the southern lobe, the southern hemisphere, and so can only be contacted with the Australia ground stations. And the Australia ground stations needed to be closed down temporarily for refurbishment. And this was a terrible time for us because we really, really, really wanted this scientific data. So first thing I did was work really hard with our friends at the Deep Space Network. They agreed to actually postpone that work on the Australia dish until we were able to actually take this data. And so every day I would get a new data plot stuck on my door at headquarters from the program scientist then, Eric Posner, watching this incredible sort of, you can see the heliospheric particles going down as the galactic cosmic rays were shooting up at the same time. And so we actually got to kind of watch it day by day until we were able to say, yes, you can see the point where it actually left the heliosphere. And then we were able to actually announce those results at the AGU meeting in Washington, D.C. in December of 2018. So it was just really great to have such an exciting thing to follow and to really feel a part of as I became the new director of heliophysics. So I also joked that I really hoped that the downward trend that you saw was not going to be indicative of my success as the director. So I hope I'm more on the cosmic cosmic ray side than the heliospheric particles. The other thing I wanted to just touch on is how the whole heliosphere actually kind of breathes with a solar cycle. And so you're looking at an animation there of, what we think the heliosphere is doing as the solar cycle ebbs and flows. So at solar maximum, the heliopause at the furthest away point, and solar minimum as it sort of breathes and comes inwards. This, of course, is quite controversial. We've only got the 2-point measurements, so it's all done with modeling, which of course Marav is an expert in. But we certainly think we see a nice pattern of the whole sort of heliosphere breathing in and out with the solar cycle. And to sort of further that, I wanted to just show you data. This is actually from our IBEX mission. And these are sort of yearly maps. And you can see there the solar cycle underneath, starting in 2004. That's the sort of dynamic pressure, the solar wind dynamic pressure. It kind of follows the solar cycle. You can see that going up to solar maximum. And there are the different sort of images of the heliosphere and how it's responding to the variability in the solar wind. And so we can actually kind of see from these yearly maps that we take with these sort of mole-wide projections of what the boundary between the solar wind and the interstellar space, what that looks like. So actually really excited. Not only do we have these great maps from IBEX, but we are getting ready to launch IMAP, the Interstellar Mapping and Acceleration Probe that will go out to the Lagrange L1 point, launching in 2025, and will take even higher resolution, very high fidelity maps, very similar maps of this to really build on what we've done with IBEX. So really looking forward to that. And I wanted to just also give you a couple of thoughts. This is actually taken from a report on challenges and strategies for supporting very long duration missions. And as we sort of think, Nick already mentioned, the idea of an interstellar probe, something that is actually built and designed to go out and leave our heliosphere. Some of the things that we really want to think about when we are planning those kind of missions. And I think this is particularly important to our early career folks that might be listening. Looking at how we do mentorship opportunities. So, how we offer graduate and postdoctoral support to keep bringing fresh new perspectives and fresh people into these missions, because these are decades and decades long missions. So, how we really want to look at bringing participating scientist programs in, how we use sort of current programs, how we kind of refresh them to keep our mission team very fresh and focused for the length of this very long duration mission. The idea of offering these sort of data analysis programs or this participating science funding to keep bringing these new members into our teams. And also for you to be thinking about how we maintain a system as we sort of keep going, how we refresh the hardware, how we keep that fresh and ready to keep supporting the mission. And also the critical thing to make diversity a real cornerstone of the team structure, because we all know that a team that represents the diversity of the current and the future workforce is really, really, really critical in making a solid team. Diverse teams are always the best teams. And so I just wanted to kind of include that to give you maybe a perspective to think about. And then I'm going to not quite finishing with this, but I just wanted to flag for you that we will be kicking off something called the Heliophysics Big Year. It will start in October of 2023 with the annular eclipse that will be visible from the US. It will include the very exciting total solar eclipse that will be visible in April of 2024. It will also include, of course, the rising phase of the solar cycle 25. And then also it will sort of finish with the final closest approach. So when we've done that the 7th Venus flyby for Parker Solar Probe, and she gets within 10 solar radii of the solar surface. And so everything kind of going on in that Heliophysics Big Year. It's a big year because it's like 15 months long. And we invite you, please, to follow along with us, get involved, tell us how the outer heliosphere is also reacting during this Heliophysics Big Year. Lots and lots of citizen science and lots of opportunities for our early career folks. So please take advantage of that and join us. And then I'm going to finish shamelessly with a plug that our decadal survey, our National Academy decadal survey in solar and space physics, or heliophysics, is actually kicking off on Monday. So the 22nd is the beginning of that panel. And I wanted to flag for you that white papers are due on August 24th. So you still have time if you are polishing them up, or if you want to spend the weekend writing one. It is so important to make sure that we have everyone's voice as part of this decadal survey, so we can really dare to do great things, dare to do, as JPL would say, dare mighty things, dare to do these really, really fantastic science, big goals in our next decade. And we want to make sure that everyone has a chance to contribute to that decadal survey. So if you're not familiar with the decadal survey, reach out to me, reach out to Linda, reach out to Marav. We'll all be happy to give you more information. And with that, I will leave you with my hashtag, and I will see if I can find the button that lets me stop sharing. Here we go. All right.
Great, and we've already got a couple of questions in the Q&A. I think we'll save those, but Nikki, feel free to go into the chat. Marav has already fielded one, and you can also use them for discussion.
Yeah, I had a hard time answering the other one while listening to Nikki, so it's like, okay, I'm stopping.
Oh, no problem. We'll get to them. All right. Linda, can you share your screen?
Sure. Can you see the screen now?
Yes, we can.
Okay. I'm going to start. Thank you so much, Nikki, for setting the stage and explaining where Voyager is today and what we're doing. And I'm going to go back in time a little bit, because it turns out that I actually started on Voyager in 1977, just a few months before launch. So I just want to share with you some of my experiences there. And for me, it was the first job out of college. I actually was looking for a job in the fall of 1976, picked up the newspaper, and there was an advertisement for jobs at JPL. So I applied, and I was offered a job, and they said, well, do you want to work on the Viking extended mission or this new mission called Voyager? And I said, well, I haven't heard of Voyager. Where's Voyager going? And they said, well, the prime mission is to Jupiter and Saturn, and if all goes well, on to Uranus and Neptune. And here I am just starting my career, and I thought, wow, a chance to visit 4 planets and places that no one has been before. So I said, sign me up. I want to work on Voyager. And so I did, and participated through the 6 planetary flybys, the amazing discoveries made by Voyager. And it was just an incredibly fascinating time. Imagine you just have, say, in a 2-week period, you fly in very close to the moons and the rings and the satellites, and that's really the heart of your data. But you've really started months before tracking the cloud structures and the various features on the planets. And it was such a tremendously exciting time to be on Voyager. And in particular for me, one piece of data was very important, and that was looking at the stellar occultation from the Voyager Photopolarimeter. It was one of the instruments on the scan platform. I actually worked with 2 of the scan platform instruments, the infrared instrument IRIS and with the PPS team. And here what you can see is the first data coming back from the photopolarimeter stellar occultation, Saturn's rings at 100-meter resolution, samples every 100 milliseconds. And of course, in those days, what we had are the CalComp pin plotters that would make these long plots of the data. And you can see everyone peering at those data. And that's what I went on to use, both the stellar and radio occultation data of the rings of Saturn, Uranus, and Neptune for my PhD thesis. And just for a little bit of context, what you can see in the panel on your right at the top is the plot of the optical depth as a function of distance from Saturn. And on the bottom is looking at basically taking the equivalent of Fourier transforms and sliding a window across the data to look for any periodicities in the data. And if you look at the top plot, you kind of get a hint of where some of the larger spikes are. There might be something going on. Those are spiral density waves created by resonant interactions with some of the small moons outside of Saturn's rings. And then the other one, just outside the edge, right edge of the plot, is the Encke gap, and a moon pan orbits inside that gap. and it perturbs the gap much like the wake on a motorboat and creates these wakes. And so the dashed and dotted lines show that these wakes actually can propagate across the spiral density waves. Spiral density waves are cool because the same physics that governs the arms in a spiral galaxy can be applied here at the scale of Saturn's rings to these spiral density waves. And I just show this plot because, you know, sometimes some of the Voyager data reminds me a little bit of this stellar occultation data of Saturn's rings. And I actually use these data to get my PhD from UCLA in geophysics and space physics. I've now come full circle. I'm back on Voyager again. I spent 30 years on Cassini. After those exciting flybys, went off to work on the Cassini mission from the mission concept through the end of the mission. And I'll have to tell you, I never thought Voyager would outlast Cassini. And so here it is, and I have a chance to come back and work on the mission again. And it's just so tremendously exciting. And Nikki's already covered those two crossings. She showed this figure, just so exciting to be out in the interstellar medium. And in fact, Voyager's legacy really stretches across the planetary missions. In particular, Cassini is a direct, descendant, a daughter of Voyager, in that the Voyager 1 flyby of Saturn had a very close flyby of Saturn's moon Titan. The goal was to see through to the surface of Titan, this thick, cloud enshrouded, very kind of smoggy atmosphere. And it turns out that the Voyager cameras and the instruments on board, the cameras didn't have the filters. The instruments weren't in the right wavelength range to penetrate through and see the surface of Titan. Titan's about the size of the planet Mercury. And so immediately after that Voyager flyby in 1980, scientists got together to propose a mission called Cassini to carry a probe named Huygens that parachuted down to the surface of Titan. So Cassini is a direct descendant of Voyager, as is Galileo, and also the Juno mission. And as Nikki pointed out, the two Voyagers are the only spacecraft directly sampling the interstellar medium. And so if you think of yourself riding along with the two Voyager spacecraft, in a sense, we've become interstellar travelers with the Voyager missions for the very first time. And one of the questions that Nick asked me is, what do I think is one of Voyager's biggest discoveries? And for me, I think it was the discovery of volcanoes on Io. Here is this incredible moon in the Jupiter system. It's actually in resonances with some of the other moons, and that makes a slightly eccentric orbit that causes the moon to be squeezed as it goes further and closer to Jupiter. And that squeezing heats the interior. You see a beautiful view here of a volcano on the limb, that's Loki. And also you can see Pele erupting, and that's sort of that ring shape with the black thing in the middle. That parts of Io's surface are only hours old. And so this really led to a major paradigm shift. I remember before we got to Jupiter, the thinking was, well, the moons are going to look a lot like our moon. That was the one example that we had. We could see up close, and we could see a little bit about the Martian moons, but pretty much old surfaces, heavily cratered, and how different the moons looked in the Jupiter system, from volcanoes on Io to a bright white icy surface on Europa with relatively few craters and fractures, Ganymede, so many interesting moons. And so Voyager's flybys of these planets, and in particular of their moons, really caused a paradigm shift, a major shift, that outer planet moons can be active, and they come in all different sizes in which they can be active. And I really like this plot. It shows the Earth and then some of the moons that Voyager visited to scale. You can see they range in size from tiny Enceladus to Titan, which is about 10 times larger in diameter. And we think from measurements that have been made by subsequent missions that these are possible ocean worlds. The oceans are underneath a thick icy crust, and these would be oceans of liquid water. So 3 at Jupiter, Europa, Ganymede, and Callisto, Enceladus and Titan. At Saturn, in fact, Cassini discovered that jets of material are coming out of Enceladus's south pole. We actually flew the Cassini spacecraft through that material and sampled it and got a measure of what the ocean is like underneath the surface. And then Neptune's moon Triton. Voyager saw geysers on the surface of Triton erupting as we flew by this moon. And so with these moons with liquid water oceans, that opens the door to questions of potential habitability, and to make, in particular, some of these ocean worlds. Europa will be visited by the Europa Clipper mission, and there are future mission concepts to go back to Enceladus as well and really dig down deep and see, are these moons habitable? So I would say that those first kicking off with those volcanoes on Io really started to change the way we looked at the moons in our solar system and where life might evolve. You don't necessarily have to be a planet in the Goldilocks zone like the Earth is to have liquid water on your surface. Perhaps with water underneath your icy crusts, you might be able to support life as well. Looking in the interstellar mission, when I came back to Voyager, this really caught my eye. Here are 3 years of data from the cosmic ray spectrometer, and it shows that the cosmic rays, electrons in particular, have a quasi-periodic behavior. I looked at those data and I said, you know, that kind of reminds me of some of those periodic structures in Saturn's rings. And I can't help but wonder what kinds of resonant interactions or what could be going on in the interstellar medium and galactic space that could create these kinds of structures. And so with continued data collection, perhaps we'll be able to figure out this puzzle. And these data aren't yet published, but I did get permission from the CRS team to show this particular plot. And finally, for future missions, focusing on planetary, we have, of course, Interstellar Probe coming up to go out and visit where Voyager is today. But there are other mission concepts, including a flagship mission to Uranus with an orbiter and a probe. The planetary decadal just came out, so I know how important these decadal surveys are. And this came up as the #1 flagship mission in the next decade. An Enceladus Orbilander to orbit and then land on the surface of Enceladus, carrying sophisticated instruments to make measurements for the possibility of life. Europa Clipper, of course. At Saturn Atmospheric Probe, we have only had probes into Jupiter's atmosphere with Galileo. So that leaves Saturn, Uranus, and Neptune still to be probed. And of course, the very exciting Dragonfly mission to actually take a quadcopter to land on the surface of Titan and land in multiple locations, taking direct measurements of the surface of that world. So a lot of very, very exciting potential missions that are really all standing on the shoulders of Voyager. And it's just so wonderful to be back to Voyager and see what else we might find. What's right around the corner as these 2 interstellar travelers continue their mission into interstellar space. Thank you.
Linda, thanks so much. When they were looking at the strip plot, is that you in that picture as well?
I'm not actually in that particular picture, but I was there. I was there watching, and I almost felt like we would unroll it and walk through it and take a pencil and circle the interesting places. And it really felt like walking through Saturn's rings.
Nice.
Fantastic. Okay, let me try to share my screen. So first of all, I wanted to thank Nikki and Linda for coming and sharing their memories of Voyager. And I think will be a good segue to what they talked. I'm going to start with some personal memories of Voyager and then segue into some of the science that Voyager did. And I think would be a good complement to what Linda highlighted. So, I showed a similar slide in the Voyager team, thanking them for these years of wonder. I came into space physics, Working Voyager was, this is my, before I go into it, I just wanted to mention, before I go to the history, how did I get into Working Voyager? When you talk about mentoring, and this is a cornerstone of SHIELD as well, you ask who were your mentors, what your support system. And I found myself every time coming back to that idea that because I'm a twin, and I'm showing here my twin when we are back in Brazil, and now she's also a professor, and my dad was a professor. They were that, cheering team that no matter what was happening, whoever was screaming at me, whoever was throwing tomatoes of whatever crazy ideas I had, I would just step out, call one of them, and they would say, come back to the ring, you can do it. So that support system, and I'm very grateful to them. So we can talk in another time of the importance of having a strong support system. Anyway, so I got into Voyager back in 2001, and only in 2006, Ed Stone welcomed me to the first Voyager SSG. I can't tell you how overwhelming it was to come to one of these team meetings. Linda, probably you felt similar, but I felt I was crashing a party that was going on literally since the 70s, right, so for decades, and people that were finishing each other's sentences, and was completely overwhelming. Anyway, since then, and when I got to Voyager was just before, actually this is 2006, but my first Voyager SSG was just before 2005, the crossing, 2004, the crossing of the termination shock. And as the years went by, I realized this is so historical. I should take pictures of some of the team meetings. So I have some of my pictures of the Voyager SSG. This is Don Gournett describing the radio waves in the local ISM. Basically, this was the data that sedimented. We were out in the ISM. I'll come back to it in a minute. And, you know, the Voyager, and I will talk a little bit about the science, but the Voyager collaboration extended all around the world. Here I'm showing a team that we put with the late Randy Jockopy and others in EC Bern, discussing these very puzzling measurements. And here we are discussing the so-called Sun heliosphere. The first time I presented it was a major controversial. And I wanted to show again another Voyager team meeting and highlight a little bit of the science. So one of the beauty of Voyager, and I will start right before I came to the Voyager team in 2004, when Voyager 1 crossed, and then in 2007, Voyager 2 crossed, is that we used to joke in the Voyager science teams that every 6 months you will have a science meeting and all your ideas you have to throw in the trash. So you will spend 6 months trying to explain the latest data, and 6 months later, you know, you will get to hear from the PI of the instruments, and all your ideas were out of the window. And you know, this was my first mission I worked on. I couldn't believe that this was going to keep going for 20 years. So since I got into the field, every 6 months there was a new surprise. And Ed Stone kept telling me, well, nature is way more creative than your theoreticians or modular ideas. And it's true. And I think that for the legacy of Voyager, we just, you know, had a first glance of the iceberg of what is a heliosphere. We just went through the termination shock, the Heliosheaths. We are in the ISM, but there is so much more to do and understand this area. So I cannot really talk about all the science puzzles, but I just decided to pick some of them. One interesting tidbit that was unexpected, that the heliosphere as a whole is asymmetric. And Voyager 1 and 2 measured it. Voyager 2 measured the termination shock, the largest shock in the solar system, 10 AU closer to the sun. And even when you account for solar cycle effects, as Nikki showed, the breathing in and out, you cannot account for that asymmetry. So something else had to be, you know, provoking that asymmetry. This was actually my first paper in the field when I worked with Ed Stone. We were trying to quantify this asymmetry, and there were other papers that suggested that could be the interstellar magnetic field, but we were trying to make it quantitative and compare, and we had a prediction that Voyager 2 was going to cross closer to the sun. And the idea is that the magnetic field that comes from the galaxy, it's almost like your hand punching a soccer ball sidewise, and the southern hemisphere is pushed in towards the sun. It's pretty amazing, I have to say, when I worked on this data, that you are on board of Voyager 30 or 40 AU before you cross into the interstellar medium, and you can sense this asymmetry. you're talking about AU asymmetries, and you can sense it. You can sense in the detectors of Voyager. That completely blew my mind. Another big surprise of Voyager that now is well accepted, but was a big surprise when the data came in, that the termination shock was not like the shock that you see near the sun. It was much weaker. And in fact, here, this is a plot from John Richardson showing the temperature that was seen in Neptune in black here in the bottom panel. And you expected for a typical shock to see a large decrease in the velocity, a large increase in the density, and the temperatures around 10 to the 6 Kelvin. But when the data came in, the temperature was much colder. The temperature measured by Voyager was an order of magnitude colder. And this was initially a surprise when people remember this is not your typical shock, but actually is mediated by the fact that the heliosphere doesn't lie into an ionized matter outside the heliosphere, but it has hydrogen atoms that make their way into the heliosphere, get ionized, and end up influencing the termination shock. Not only that they influence the termination shock, but those thieves that come from the galaxy ended up stealing all the energy. So all the energy in the Heliosheath is dominated by the thieves that came, the hydrogen atoms that came from the galaxy. So it's pretty amazing. It's a complete new regime of physics of a very slow wind dominated by hydrogen atoms. Okay, so this was a huge surprise. Then we got into the Heliosheath. So you thought, okay, now I can open my books and I know everything about the subsonic fluid and I can compare the models. But lo and behold, when the data came from the flows measured on Voyager 2, so as Nikki said, the Voyager 2 has a plasma instrument that can measure directly the flows of the plasma. Voyager 1, you had to infer the flows from the energetic particles, so it's an indirect measurement. But when you compare the two flows, and you compare those two flows with models, nothing match. So both flows, Voyager 1 and 2, are drastically different. The flows on Voyager 1 after the shock shown here in 2008 went around 100 kilometers per second and decreased all the way to the crossing of the Heliopause to very, very small values, almost zero, while Voyager 2 stayed around 100 kilometers all the way to the Heliopause, almost not even realizing there is a boundary to be crossed. This is a major puzzle. And now there is even a revisit of this data. And this is, I think, one of the exciting things on Voyager, that even after 45 years, you go back to the data and you challenge the data. You said maybe these inferred speeds by the energetic particles might not be right, or might be telling us about some physical phenomena that we were not aware. So I think this data of the flows is really exciting, and it's pointing to some critical physical phenomena that we're not understanding. One interesting thing that the flows again told us, those the one inferred by Voyager 1, that there was a region where the flows of the solar wind went to zero. That was called the Stagnation Region, a very unusual region. If it's real, it's very, very interesting. Neither of the models predict that. The fact that the solar wind can stop for a couple of years before being deflected of the boundary is a major puzzle. Now, when we cross the Heliopause, as Nikki was describing, first with Voyager 1, and I think this is one of my dearest moments, the crossing of the Heliopause. There was a journalist just asking me this week what year was the major event, I think, in this crossing, because it's felt to me like, imagine you're Christopher Columbus sitting on your vessel, looking at the Americas and saying, I don't know if I see a new land. I cannot even declare that we really crossed for the first time the heliosphere. So this lasted for a year, that the Voyager team pored over the data and couldn't announce if we crossed the heliosphere or not. And again, it's a testimony how nature is complex and interesting. Before we cross the Heliopause, the cosmic rays from the galaxy, you can see these two peaks, made their way inside the heliosphere, and the solar wind leaked out before in this bottom panel. for a couple of times, twice before totally left the heliosphere. I like to think it's like the heliosphere opened the window and let the material from the galaxy come in and the solar wind come out before we left. So this just tells us that this area, it's very porous, much more complex than books or what we thought the Heliopause is. And the major challenge, I think, for the theoreticians and for the observers was you had the expectations that across the Heliopause, the magnetic field will rotate. And the magnetic field inside, of course, is solar, and it has this direction shown here, left to right, where the interstellar magnetic field is inclined at least 60 degrees to it. So you expected an abrupt rotation, and this was not seen. And this was one of the puzzles why the Voyager team couldn't announce a crossing, because there was no rotation. I won't go into all the details here, but as we went through the Heliopause, the angle shown here on the bottom panel didn't change at all. And the other super interesting, and I'm going to wrap up, is that the angles didn't change much. You go in Voyager 1, we are now almost 40 AU beyond the Heliopause, and the magnetic field has some variations in intensity, but the angles are steady rock, and they're vastly different than what we expect in the ISM. So why is that? And are we going to see a rotation? When it's going to happen? It's another puzzle. So I think, again, testimony of Voyager, the puzzles keep piling up, and the surprises keep going on. And of course, there is also this big debate on the very shape of the heliosphere that the community is trying to answer. So this is a plug for the center that we're trying to lead with the observers of Voyager and IMAP, in the preparation to IMAP, and observers from IBEX, from New Horizons, trying to pour through this data and having the power from different theoretical and modeling techniques to try to have what we call a twin analog of the heliosphere. Try to look at the data and at least start checking off some marks that we really understand the heliosphere and the heliosheath. And of course, this is my last slide. The big question is, once we understand the heliosphere, this is the only habitable astrosphere that we know of. And even if we find another Earth-like planet, it will be within an astrosphere that we won't have an in situ data as Voyager. And Voyager showed us that even with a beautiful line of sight images, there's nothing like in situ data to tell you that all your theories are wrong. So I'm going to stop here, and we can open for questions.
Great. Thank you to all of our speakers for these wonderful presentations and this retrospective on Voyager, and looking forward to the future. There's a few questions in the chat. They've been or in the Q&A section. Please put more in if you have them. At least, so a number have been answered already, but we can revisit them. At least one of them is like was asking about Nikki's comment about the Heliophysics, the big year of Heliophysics. What sort of following on to that, certainly Marav and Linda talked about coming into a high-profile mission in terms of Voyager. Nikki, I'm sure you had similar sort of experiences. What is that like? How do you do that, right? How do you like say, hey, I want to work on this thing that everybody's excited about?
I think you say those exact words, Nick. I mean, you seriously, most mission teams welcome enthusiastic people that really want to work and want to jump in and work on the data. And so really expressing an interest in finding a mentor. You know, Marav mentioned how important mentorship is. I sort of flagged it as the importance particularly for these long duration missions. And anyone who knows me knows I'm a big fan of mentoring, and finding a good mentor and just really showing that enthusiasm that that's what you want to do. And I will say, if it's a heliophysics mission and you want to work on it and you don't get an enthusiastic response from the team, please send me an email.
Okay, well, that's a direct invitation. Marav or Linda, do you have
I just had a comment for another question, but I will let you, Nick, pick. I just noticed that Brian Field was asking, and Brian, you can chime in, about if, to what extent interstellar space was part of the Voyager design, and it was not. And actually, neither the interstellar space, neither the Heliosheath. And this is one of the challenges, that the magnetometer is, measuring fields on the order of 0.1 nanotesla when the noise is 0.05 or 0.08. So you're right at the noise. They were designed to measure much more intense magnetic fields. Also, Voyagers are not measuring those thieves that I mentioned, the pickup ions, that are the main contributors in the Heliosheath. So they were not designed for the Heliosheath or even the distant solar wind. New Horizons will be the first spacecraft to measure in situ pickup ions.
Right.
So
Yeah, I
it's
would
really
add.
serendipity into the creativity of the Voyager team that they were able to work. Yeah. Yeah, go ahead, Linda, sorry.
Yeah, I would add that the prime mission for Voyager was initially 4 years. And so I remember at the time when we got to Uranus and finally Neptune, the talk of how old the spacecraft were and how far we were past that, prime mission. And so we've lasted 10 times longer. And that's really a tribute to the engineers who built the spacecraft and really had to help radiation harden the components for the Jupiter flyby. And so I think that's standing us in good stead now, being out amongst the much increased density of cosmic rays.
Yeah, thanks for that. And thanks for your wonderful recollections and these exciting pictures from the 70s. So at the time, did people even dare to think about that you could get as far as interstellar space and still communicate back?
Not even close. It was not until after the Neptune flyby with 2 healthy spacecraft that we then started to seriously think about a Voyager interstellar mission. What was so amazing at that time, we didn't know where the Heliopause was. And at first there were thoughts of, okay, maybe it's out twice the distance of Neptune or something like that. And then finally, Don Gurnett, there were some really large events on the sun from coronal mass ejections. He's Forbush in 1980s and 1990s, and he actually got a reflection back. And so he had a range of the Heliopause, and it was much, much, much further away than some of our initial estimates. And so it wasn't clear that Voyager would last out all the way out and cross the Heliopause. And now if you think about it, Voyager 1 crossed the Heliopause 10 years ago. And it's continuing on to explore interstellar space. And 50 years from now, Voyager 1 will be at 175 AU. And that'll be 50 AU from the Heliopause. So what will we see as we increase that distance from the Heliopause?
Yeah, and I also want to give a shout out to the incredible team at JPL who are just keeping this mission going and finding creative ways to really increase the longevity of the mission. I won't go into all the details, but I did get a presentation recently from Linda and the team, and it was so impressive to see just creative, super creative engineers and what they can do. So it doesn't surprise me that it's still working, but sure wasn't planned.
And it seems like from some of the comments in the chat that the fact that it went out the nose was it a complete accident, or do we have any idea that there was such a thing as a helio nose, or?
I don't know if the time of Voyager launch, if we really understood nearly as much as we do now about the heliosphere. It was just, that's where we were going to go if we wanted to follow that grand tour. That alignment of the planets only happens once every 176 years. So we just ended up going where we went. So that was it.
There was some older models by Axford and others imagining the heliosphere, but we had no idea. Right, I think we knew nose, but
You muted yourself, Marat.
I was done.
Okay, great.
Yeah, I think we maybe knew the direction that the sun
We
was.
knew the direction of the nose. We knew that there was a nose. I think in all the models, there was a nose. The distance of the nose, we didn't know. And
Right.
of the complexity of the heliosphere, we didn't know either.
And Jean Parker also had a wonderful paper on it. I have to mention Jean.
Oh, absolutely.
Of course he did.
Yeah, absolutely, Jean. Yes.
He had a paper on everything.
Having two types of heliosphere, two type.
Mhm.
And somebody in the Q&A asked to touch a little bit more about the IMAP mission.
Yeah, sure. So IMAP is one of our solar terrestrial probes missions in the Heliophysics division. It is a PI-led mission. So Dave McComas at Princeton University is the PI for that, or the principal investigator for that. It is being built and integrated at the Johns Hopkins Applied Physics Lab. I think it has 10 different instruments on the spacecraft. So it's very, very high quality measurements. Sort of thinking of ACE, which is our sort of solar wind measurements out at L1, and IBEX, taking those images that I showed of the boundary and kind of putting those missions together. So IMAP will sit at the Lagrange L1 point. It will actually measure all of the plasma coming from the sun. So it will measure, all the stuff that's going from the sun outwards. And then it will use these ENA imaging techniques, very similar to the mole-wide plots I showed from IBEX, but it will be doing it at 3 very sort of carefully chosen wavelengths or frequencies. Energies. It's got a sort of ultra high, which is extends the energy range above what IBEX can do, and then a sort of a high and a low energy ENAs that it will sample. So it's going to be an amazing mission, sort of putting together all of the acceleration processes, both coming from the sun and also reflecting back with our ENAs coming back from the boundary. So you can find lots and lots about it on the web. Google NASA IMAP or Heliophysics IMAP, and you'll find lots of information about that. Or just reach out to Dave McComas. He loves to tell everybody about IMAP. He's actually got a number of, actually we could probably don't know if I can find it quickly now, but he's got a couple of recorded lectures that he's given about IMAP. If I can find it before we close, I will put it in the chat. If not, I will send it to Nick and maybe he can distribute it.
When does IMAP launch?
Right now, we are on target for February 2025. Yep, and it's actually launching with two ride-alongs. It's launching with the Space Weather follow-on, which is the NOAA mission to replace Discover. And it is also carrying one of the heliophysics missions called Glide, which is going to be taking high-resolution images of the Earth's exosphere. So it will go out to L1. And if you are familiar with, I think it's Apollo 16 that took one of the very few images we have of the Earth's exosphere, took it from the moon. And Glide will actually be taking high-resolution spatial and temporal measurements, looking at how our Earth's exosphere kind of breathes with the solar wind impacts. So lots of excitement on IMAP.
Just to add to what Nikki said, what is very exciting about IMAP as well is that there are some puzzles that already, I didn't talk about it because I was focusing on the Voyager side, that you can say that IBEX, the predecessor of IMAP, showed. And I think we are hoping with a higher sensitivity and the higher extension in energy to solve. So it will be a really exciting.
Okay, we're at the top of the hour. There's always more questions to ask, of course, but I also want to be respectful of everybody's time. And so if you've got more questions, certainly put them in the chat and we'll try and handle them. But I did want to thank the speakers and put them in and appreciation for their efforts. And also, before we lose everybody, go back to our future events that are happening. I'm covering up my screen, my own screen. too many windows. All right. This is why they have professionals in studios doing this. Great. Right. So this fall, keep an eye out for other SHIELD webinars, including Vicky Calagera, and then in January, Peggy Shea, and then the SHIELD Social Hour. And I'll also invite Sandlin Buxner just to say hello. Sandlin is the SHIELD Director for Broadening Impacts.
Hello, this was such a wonderful, wonderful start to the series. And we just want to invite everyone to come back. And we are so excited for everyone in the space physics community, especially our early career scientists, to continue. So we're going to have lots of great opportunities for you to join us and just really be a part of this wonderful community. So I just wanted to say welcome to everyone.
Great. Thank you, Sandlin.
And
Okay.
I think I muted myself. I just wanted to thank again Nick and Linda for coming, the speakers. Thank you.
Thank you so much for inviting us. And everybody remember, decadal white papers, August 24th, decadal white papers.
Don't have a weekend, no.
Yeah, it was a pleasure to be here, Marav. Talking about
Thank you so
Voyager.
much. It was wonderful.
Thank you.
Yeah.
Oh, it's a pleasure. Thanks.
Okay, great. All right. I think at this point we'll bring it to a close, and again, thank you all, and look forward to seeing you all in the future.
Thank you so much, folks. Bye.
All right, bye.
Bye.